Hello everyone, and welcome to week 10 and a mini lesson on multivariate functions. So a multivariate function is just kind of how it sounds: multi meaning more than one, and variate meaning more than one variable. So we're going to be looking at functions that have more than one variable in them. Up until now, we've only been working with functions with one variable, and we've been working on taking the derivatives of those functions. But what happens if we have a function with more than one variable? How do we handle that? So I can assure you, first off, that at least the rules for taking derivatives remain the same. There's just a bit of an extension, and I'll explain that to you in this lesson. So the first thing is, now we're going to have function notation where we have two variables in the bracket. So we have f at x comma y, so that means we have a function with two variables, x and y. And what if that function looked like this? So what if it looked like 3x squared plus 4y cubed minus 8xy minus 17? So we have two variables, and we're able to find the derivative of this function just as we did with single variable functions. So our first step was always to look at the function and identify how many terms and what kind of terms, and then we can refer to the rules for taking derivatives that we know. So we're going to look, we have 4 terms, and we see no e, no ln, and basically we're looking at 4 terms that are added or subtracted together. So we have sum and difference rule and power rule. So I'm going to put this down on the bottom. Remember the power rule, x to the n, the derivative is nx to the n minus 1. Okay, so nothing's changed. We're still going to apply that rule. So how is it different? So we have two variables, which means we are able to take two partial derivatives. 2 because that's how many variables we have, and partial because we're taking the derivative of one variable at a time. When we have two variables or more, we're always taking the derivative with respect to one of the variables, and the other variables in the function are then considered a constant. Okay? So let's see, if we take the derivative with respect to x, we'd write it like this, with the little x subscript and xy in the bracket. So the derivative with respect to x. So now we're going to review the terms, and we're going to find those terms that contain an x or an x squared or some combination that has an x in it. So we look at the first term, 3x squared, and indeed it has an x in it. And so we're going to take the derivative of that using the power rule. So we've got lots of practice with that power rule, and we know that the derivative of 3x squared is 6x. We look at the next term, 4y cubed, and we say, wow, there's no x in there. And remember, every other variable but the one that we're taking the derivative with respect to is considered a constant. And we know that the derivative of a constant is 0. So that's the derivative of that term with respect to x. The next term, minus 8xy, there is an x in there, and there's also a y. Remember, the y is considered a constant when we're taking the derivative with respect to x. So this derivative here is going to be minus 8y. Minus 17 is simply a constant. It doesn't have variable x or variable y in it, and so the derivative of minus 17 will be 0. So that's the partial derivative with respect to x. The next step would be taking the partial derivative with respect to y, the other variable in this function. So again, we go through each of the terms, and we look at 3x squared, and we say, well, there's no y in it. So the x is considered a constant, derivative is 0. Plus 4y cubed, there is a y in it. We need to take the derivative of it. We follow the power rule, and we know that the derivative is going to be 12 y squared. The next term, minus 8xy, there is a y in that term. We take the derivative, now keeping x constant because we're taking the derivative with respect to y. So the derivative will be minus 8x. Minus 17, still no x and no y, simply a constant. The derivative is 0. This example here, writing a formula for a multivariate function, gives us an idea of where a multiple variable function might come from. So the question reads, find the formula c at xy, so cost with two variables, x and y, that gives the cost of materials for a rectangular fence, assuming that there is a decorative fencing cost, $20 Canadian per meter along the front and back, and privacy fencing, which costs 7 Canadian dollars a meter along the sides. It might be easier to draw a little diagram. So along the front and the back we have decorative fencing. So we're going to say X here and X here. That's our decorative fencing. And along the sides we have privacy fencing. We know that every X costs $20 and every Y costs $7. Y feet, X feet, and so on, or meters, I guess it is. So how do we develop that function? C at xy is going to be 20 times 2x, because there's an x the front and the back, plus 7 times 2y, because we have a y, length y on either side. When we simplify that, we get 40x plus 14y. And that will be the multivariate function representing the cost for this rectangular fencing around the yard. Let's look at question 2, first derivative of multivariate functions. This one is a more business contextual question. It says the profit function for a souvenir vendor is given by profit, p at x, is equal to 2x squared plus 3y squared plus xy plus 1300x plus 2200y minus 500, where x is the number of t-shirts in hundreds and y is the number of sweatshirts in hundreds. Find the profit function and interpret p sub x at 30, 5, and find the profit function and interpret p sub y at 30, 5. So exactly what does that mean? So we're looking at the profit with that little x, and that means take the derivative with respect to x. So remember, we're keeping every other constant. In this case, we only have one other, that's y. We're keeping y constant. And then it says substitute x is 30 and y is 5, and solve, and then interpret. Part B, we're looking at the derivative with respect to y, which means we're keeping x as a constant, or considering x a constant. And again, we're substituting x is 30 and y is 5. And so you're going to remember that the derivative means the rate of change or marginal value of something. So what we're going to look at is this partial derivative with respect to x. So consider what that means in the context. We are looking at the derivative with respect to x, and we're keeping y constant. So we can assume then in this p sub x that we're going to be changing x by 100 t-shirts, or in this case 300 or 3,000, but we're going to keep the number of sweatshirts constant. And so how is our profit going to change? In B, we're taking the derivative with respect to y, So that means we're changing y, again, in hundreds. So in this case by 5 times 100, so 500, but we're going to keep x constant. And we're going to look at then how the profit changes. Okay? So the first thing is, let's find the two partial derivatives. So we have p at x of xy. So just like in our prior example, we're looking at each term, we're identifying each term, and we're taking the derivative. And again, if I scan them quickly, we have 1, 2, 3, 4, 5, 6 terms. All of them appear to be power rule. So we're going to use our power rule. Remember, x to the n, derivative nx to the n minus 1. Okay, so the first term, 2x squared, we have an x in it, so we are going to need to take the derivative of that, and that is 4x. We look at 3y squared, and there's no x, so we treat y as a constant, so that the derivative of 3y squared is 0. Plus xy, we have an x, and again y is considered a constant, so we only have the y left when we take the derivative. Plus 1300x, the derivative of 1300x with respect to x is 1300. 2200y, well, it doesn't have an x, consider it a constant, derivative of a constant is 0, and minus 500, derivative of minus 500, because it's a constant, is also 0. Okay, so now we look at the derivative with respect to y. We go through the same process again. First term, 2x squared, there's no y in it, so we don't take the derivative is 0, we consider it a constant. 3y squared, okay, there is a y, we need to take the derivative of that function, and that's going to be 6y. Plus xy, we have a y there, and x is considered a constant, so the derivative of xy with respect to y is x. Plus 1300x, there's no y in that term, so it's a constant, derivative is 0, plus 2200y, so we have a y there, and the derivative of that with respect to y is 2200, and again minus 500 is a constant, so the derivative is 0. So that is finding the two partial derivatives. And now it says evaluate them when x is 30 and y is 5. So I'm going to take that over to another page where we have lots of room to do that. Here are our two partial derivatives, p sub x, the derivative with respect to x, and p sub y, the derivative with respect to y of the profit function. So the question asks us to evaluate it at x is 30, y is 5. So we're going to say p at x at 30, 5. So everywhere we have an x, we substitute 30. Every place we have a y, we substitute 5, just like we've been doing all along. And this totals 1425. It's the profit, so it's in dollars. And in the first derivative with respect to y, we do the same thing. P at y of 30 and 5. So 6 times 5 plus 30 plus 2200, and that equals 2260. So to interpret this, we're going to say that the increase in profit if t-shirt sales increase from 3,000 to 3,100, because the numbers of t-shirts are in hundreds, will be $1,425 when the sales of sweatshirts remain constant at 500. For the first derivative with respect to y, that means that the increase in profit if sweatshirt sales go from 500 to 600, while the sales of t-shirts remain constant, will be $2,260. From here, you can go to the other video question solutions and work on those, and I'll see you in class.